Hi friends, welcome to the channel Learning R is Fun. In our last video we have covered ANOVA statistical test, and in the previous videos we have covered non-parametric and parametric tests. Before we continue with this some of the tests, we need to know what is contingency table, and in today's video we will cover a contingency table. Contingency tables have been formulated by Carl Pearson, who is an English mathematician who founded mathematical statistics, and basically this cross tabulation helps us to condense data, a large number of observations, in smaller and easier fashions. Contingency tables are used heavily in various research, business intelligence, etc., and it's a way of summarizing the categorical variables. There are several functions in R which will help us to formulate the data in terms of tables. We have already seen table and tabulate and other functions. Similarly, we can see some other functions in today's R Studio. We got margin.table, we got F table, that is to formulate the tables nicely. Xtab, basically it is for cross tabulation. And then we got other functions, similar functions like cross table from different packages. There are certain statistical tests you can perform only after getting the contingency tables. Some of the tests have been given on the screen. Chi-square test is something which we will cover in the next video, and I will give some idea of Fischer's exact test, which is also a type of independence test. We have already done t-tests for independence, and Bernard's test is an alternative to Fischer's exact test. There are certain tests which are using three-way contingency tables. With this background, let's go to R Studio. As usual, I have kept the code for today's session in the editor. We will create three objects, var1, var2, var3. We will use sample function. In the first case, we will choose between male and female and we will create 10 data items. Then similarly, A, B, C, 3 letters, we will create 10 items. var3 will create yes or no. So from this we will create a table, and table will give var1 and var2 only will take, and we will create a table, my table, and let's look at the my table. So between variable 1 and variable 2 the data has been, you can say, condensed, and we are seeing that in female and male between ABC the frequencies have been calculated and we are getting it. Now from this table we can also create a margin. When we say margin, we are basically summing over the row or column. So for when we say 1, then it means summing over row. So margin.table does this work. So we can see for female the row total is 1 and the male row total is 2 plus 1 plus 6. We have got 9 here and here we got 1. That's what we are getting here. The same thing we do with the column. Then we can expect here 1 plus 2 3, 0 plus 1 1, and 0 plus 6 6. So we are able to do this. Similarly, we can have proportions also. So prop.table, again we give my table, then immediately we get the percentages here. That is, the total value is found out, like in this case 1 plus 9 10, total value is 10. So 1 by 10, 0 by 10, 0 by 10, 2 by 10, 1 by 10, 6 by 10. These are the values you see here. So 1 by 10, 0.1, 0 by 10, 0 by 10, 0 0, 2 by 10 it is 0.2, 1 by 10 0.1, 6 by 10 it is 0.6. The 10 is the total of all these things. So we are getting a table of proportions. Again we can get a table of proportions only for a row, that is we get row percentages, and then here what has happened is the total is 1, and in 1 the 1 becomes 1, that means 100%. Here this 0 is 0%, 0%. Here we are having total 9, 6 plus 1 7 plus 2 9. So 2 by 9 into 100 is what you get here. 1 by 9 into 100 is what you get here, and 6 by 9 into 100 is what you get here. So you understood how the row percentages are being obtained. Similarly, we can use prop table with the column percentages. Total is 3, so 0.3 and 0.66. So you get this 100% here. Again, here is 100% here, 0% here. Here 100% here, 0% here. So that's what we get. So you can understand these functions very easily. Now we'll go for three-way frequency tables. We already created var1, var2, var3. So now we'll create a my table using all the three objects. So now let us look at my table. We are getting an array. My table, that is here we are seeing comma, comma and var3. That is first two dimensions we are going to explain. The third dimension is var3 is no. In this table or in this matrix, we can say the first two dimensions will be putting in the table, and third dimension var3 is yes. So we have got arrays in which two matrices have been created, and we can see this kind of input. If you ask string structure, then you will get it's a integer table integer with these dimensions. Now there is a function called ftable. Basically it's going to help us in flattening this entire thing, and we can see precisely in a nice form the same data. But before that I have asked R what is ftable. It is saying flat contingency tables. Here description, ftable creates flat contingency tables. Basically displaying a contingency table in this flat matrix form via printf table. The print method for objects is often preferable to showing it in a higher dimensional array. That is, the data can be shown in this fashion like arrays, or it can be shown as ftable. So ftable my table itself will give the result, but I have to print also. So you are getting the same data represented in summarized together. Now the same thing if you represent using data frame, how does it appear? So my data will use cbind and bind all the three columns, and then let us see what is my data. So what we are seeing here, this data is what is summarized and kept here. Now let us look at X tabs. X tabs basically the cross tab. So this function we can give a formula type input here. So there are three variables. So I am giving my table, I am going to coin using X tabs function with a formula, that is var1, var2, var3. All three have to be together. Means all have to be taken into account while creating this summary in my table. So let's look at my table. My table has given the same arrangement as we have got earlier, the matrices. Now we can ask ftable to print this. So you are getting ftable, the same two arrays have been put together. I mean two matrices have been put together, and then we are getting a flat table. In the flat table, we can arrange the variables in the manner we like using a function called upperm. Upperm is basically a permutation rearrangement. So you can say here array transposition. Transpose an array by permuting its dimensions and optionally resizing it. So here what I have given, I have got a my table here, and that my table is an array in which there are three variables, and now I am saying the second variable and third variable should be put in the form of table, and the first variable is the last dimension. So with this what happens? Now let us compare the two arrangements. Here we are having var1 that is female and var1 as male. So between this general classification of var1 male and female, the other two variables var2 and var3 have been tabulated, and previously here we got them like this. var1, var2, var3 were used in this formula. So the var3 has been taken as the decision for each matrix. So var3 as no and var3 as yes, and then var1 and var2 have been combined. But here it is done in different way because we wanted it in this fashion. So we said the 1 should come here, that is the decision which matrix, how matrix is to be formed is filtered basically first attending to the last dimension. After attending to the dimension filter, then remaining data is summarized. So that's how it is being done. We'll continue our discussion with Fischer's test, which uses contingency table. We'll ask R, what is Fischer's test? Performs Fischer's exact test for testing the null of independence of rows and columns in a contingency table with fixed marginals. That is what R says. And now for a first example, we'll have to load a package called VCD, and you have to install it first. Then let's load it. I've done the installation already. Now we'll ask what is arthritis, which is a data set. Then R explains data from Koch and Edwards from a double-blind clinical trial investing in new treatment of rheumatoid arthritis. The data is having patient ID, treatment factor, indicating treatment, either placebo or treated. Then sex is factor indicating sex, female and male, and age of patient. Improved order factor indicating treatment outcome, none, some, marked. There are 3 possible values. So let's see some data of arthritis, 84 rows, and we have got the data here. Now we will perform Fischer's test, arthritis treatment for column and arthritis improved column. These are the things we are going to give. And Fischer is telling it's a p-value of 0.001, which means we have to reject the null hypothesis and we can accept the alternate hypothesis, which is two-sided. What we understand from this is that there is definitely an effect because of the treatment. So we'll move on. We'll see another example. Here non-smoker data, smoker data is given, and they belong to athlete and non-athlete. So we'll first create the data. Now we'll ask what is my data, which is obtained by combining. So we got a cbind function combining non-smoker and smoker, and then we have given row names which are available here, athlete and non-athlete. We have got a contingency table here. We can also try a chi-square test, but in chi-square test the contingency table should not have value less than 5. Here this table, this is one table actually observed. Then we have to find a expected value contingency table also, that can be obtained using $expected in chi-square test. When we do that, we are getting a contingency table of expected values. These are observed values, these are expected values. In the expected values, you find a value which is less than 5. Therefore, chi-square approximation may be incorrect. That is what R is telling us. So we can do Fischer's test. So we'll do the Fischer's test for my data, and we are getting a value 0.02, which is less than 0.05. So we reject the null hypothesis. And in this case also, we can confirm that there is definitely an effect between the smokers and athleteship, Basically, if you are an athlete, you tend to not to smoke. That is what we get from this. In this example, there is a British woman who claims that she can find out whether in the cup tea was poured first or milk was poured first by tasting it. So the data is given. So let's just load the data and then look at the data in the form of a contingency table. Here her guess is here, actual truth is here. She guessed it is milk and out of 4 times she was correct. She guessed tea and out of 4 times she has found out correctly 3 times. So it's 75% success. But let us see whether Fischer's test is giving the same result. It is giving a value more than 0.05, which means we have to accept the null hypothesis. So even though it is 75% what we see here, at 95% confidence level, we are not able to accept the claim of this lady. Okay, there's an example in R help which is giving us more dimensions of contingency table. We'll try that. So there's a data given for income and satisfaction. So let's load it as it is and then see what job is. So we have got a data set here. Income is given here, very disappointed, little disappointed, moderately satisfied and very satisfied. These are the data values available. Now let us do the Fischer test on this job data. It is giving us a value 0.78, which clearly means that we can accept the null hypothesis. So null hypothesis basically implies here the income and satisfaction of a job, these two are not connected. And the same data can be, same decision can also be obtained using a simulated p-value, that is Monte Carlo simulation, or provides for that. Here let us see what is the value. The value here is again p is 0.78, which indicates again the job satisfaction and the salary or the income. These two do not correlate, or in other words, higher the income, higher the satisfaction, you can't say. So that is the finding here. So in all these examples, the theory behind Fischer's test has not been explained. What we are trying to say here is how it is easy to use a Fischer's test. There are arguments like what we have seen in the last case for Monte Carlo simulation, and there are other arguments for various requirements. So these things have to be read from the help and then you have to read statistics. But R provides all the possibilities. Using different arguments you can achieve that. So contingency tables are necessary for certain tests. One test which is very important test in statistics is what we are going to see in the next video, that is chi-square test, which utilizes the contingency table of observed values and expected values. So till then, bye from me. Thanks for watching.